Welcome back, everybody. So we saw transfinite induction. Now we're gonna see transfinite recursion, right? Remember, for the natural numbers, we have those two things. Induction is to prove things, and recursion is to build functions. And induction is to prove things, assuming you know that all the previous values satisfy your property. You want to use that to prove the property for the next value. In transfinite recursion, you want to define a function. You assume you have already defined the function for the previous value, and you define it for the next value, right? So that's the same idea in both cases. Natural numbers are and ordinals and well ordinals. So we need this piece of notation. Remember, b to the a is a set of all the functions from a to b, and we're defining less than a to the b, and this is the set of all the functions whose domain is of the form seg t, so the initial segments of some t, below some t, and the range is included in b, right? So I guess this is equal to the union of seg t to the b, so meaning the function from seg t to b for t in a, right? So it's all of those possible sets together. So just as an example, if you take less than omega to b, what is this? This is the set b0 union b, union b1, union b2. So it's a set of finite. It's a set of finite tuples from b if you take omega. But here we're taking a larger, I guess, orderings a than omega, or smaller, either way. Okay, so that's what that notation means. And here is recursion principle. Again, the idea before we read this is that suppose you have a procedure you want to define a function, and at each point when you want to define it, you have a way to define it using the values of the function at the previous values. And you want to use those to define the new one. And the transfinite recursion principle tells you that if A is a well ordering, then yes, you can do this. So here's the statement. So suppose you have this function g, which here is just a function that you have to imagine. This is the procedure. This is the procedure that tells you, given what's been defined so far, how you define the next step. And it goes from the set of functions from initial segments of b to b. And given that, what you get, this is the object you're building, is this function f from a to b. That's what you want to build, which satisfies that at t is equal to what you get by applying this procedure g to the restriction of f to the previous values, right? So remember, this means f restricted to the previous values. You forget about the values of f below. So the graph of this is essentially, if you guys remember, this is if you see it as a graph, this is a set of all pairs a comma b such that a is below t, or belongs to the segment of t, and b equals a of a. So it's the restriction of the graph only to the things below t. And this g is kind of this procedure that, if you know what f does in the previous cases, tells you what to do next, right? So this is essentially what we did for the natural numbers. And it's a bit more complicated for a general well ordering because these well orderings can be anything. All we know is that they satisfy this property that every subset has the least element. Is definitely, this is not the definition of f right away. You need the principle, because here you're using f on one side and on the other side of the equation. So you're using f to define f. And that shouldn't be good. The point is that you're using smaller values of f to define the new bigger value of f. And why is that? You know that's going to be okay, because for define this value, you're using the previous value, and to define that one, use the previous value, to define that one, use the previous value. So the fact there is a well ordering means that this process is going to be finite and it's going to end eventually, and you're going to be able to define your value. The proof is a bit tricky, and we're going to do it in a minute. But before, well, maybe in a couple of videos. But before, let's look at just a simple example. So let's consider A to be the linear ordering that corresponds to omega times omega. Ordered lexicographically like we did in the example in the previous video. So you first look at the first coordinate, compare that one, and if those are equal, then you look at the second coordinates. If the first one are not equal, you're done. And let's define this function like this. And I claim that this definition kind of fits the transfinite recursion. Let's see what this is doing. So here we have a picture of omega times omega. And the order again is first look at the first coordinate and then look at the second coordinate. Let's start figuring out the first few values. So first, f of 0, 0 is not well defined there, so we need to add it here. So let f of 0, 0 be 0. Sure, 0 real number. What is f of 0, 1? So this one here is 0, 0, here is 0, 1, here is 0, 2, here is 0, 3, 1, 1, 0, 1, 2. So what if f of 0, 1? Well, if the supremum of the set, well, it's only one element below 0, 1, which is 0, 0. So f of 0, 0 essentially plus 2 to the minus 0. And that is equal to 2 to the minus 0 is 1. And f of 0 is 0, 0. So that's 1. So this one is 1. Right? Now, what is the next one? So f 0, 2 is the supremum of the things below 0, 2 right there. So it's equal to, I guess the case, let's just write it down, f of 0, 0 plus 1, comma, f of 0, 1 plus 1 half, 2 to the minus 1, which is equal to 1.5. f of 0, 3 is equal to the supremum now of this guy, and f of 0, 2 plus 2 to the minus 2, which is equal now 1.75. And you can probably guess where we are going with this. F of 0 n is going to be equal, well, I'll let you guys calculate it, but essentially it's going to be equal to 2 minus 2 to the n minus 1. Okay, that's what you get. So it's getting closer and closer to 2. And now when we do this guy, the next one, who comes next? Well, this is the guy that comes next in the ordering, right? 1, 0 is the one that comes next. So dot 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 f of 1, 0 is going to be the supremum of f of 0 n plus 2 to the minus n for any of the natural numbers. So it's the limit of that, and that is equal to 2. And then the next one you're gonna get here 3, 3.5, 3.75, dot dot dot, and then you're gonna get the limit, and you're gonna go up here. It's gonna be 4, 5, 5.5, 5.75, dot dot dot. You take a limit. You're gonna go up to here is 6, 6 point, and then you get 7. 7.5, 775, 8, and so on and so forth. So you guys see how this is built by recursion? So work it out. Try to work out those numbers that I just did and see if it makes sense. Remember the ordering on these guys come like this one is less than this one is less than that one is less than that one. And once you're done, it comes up and it continues up here. And then you continue going up, going up, going up, and then it continues. That's the ordering. So you go to infinity, and then you go in the next level, and then you go to infinity, and then the next level, they go to infinity, the next level. So that's the ordinal, that's the well ordering omega times omega. And that's how you define this thing by recursion. Let's work a little bit more with this example. How is that we can write this example in the setting of the Transfinite recursion principle? So what is G up here? So I claim that G is this function. So G is supposed to go from less than A into the reals to the reals, right? In this case, we're talking about functions to the reals. And what so G does when it takes a function H, so remember it has to take something from here. What G does when it takes a function H is to take the supremum of H of x plus 2 to the minus pi 2 of x. What G does when it takes a function H that comes from a set of initial segments, from an initial segment of A to the reals, is the following. It takes the supremum among all the x's in the domain, all the x's in the domain of H, of H of x plus 2 to the minus pi 2 of x, where this pi 2 is the projection into the second coordinate, right? Pi 2 of AB equals B. So that's what H does. So you input a function whose domain is only an initial segment of A. What it does is take the supremum of all those values plus these 2 to the minus second coordinates, right? And then that is exactly what this is doing. We have to always add, well, always add. In this case, the case 0 doesn't work because you get the empty set. So you need to add that to the definition. And then you see how this definition up there is a particular case of the Transfinite recursion case. Yeah, you get that that's exactly an application of Transfinite recursion. Good.